I will begin. Heavenly Father, we thank you for this day again, Lord. I thank you for these students. Thank you that you loved us even when we didn't love you, and that you're such a good and kind and gracious God. Help us to understand the math we go over today, and just bless this work, Lord. In your name I pray. Amen. All right. I think last lecture is actually pretty much fine. The main distinction between us and Nicholson is Nicholson defines the principal ideal generated by an element of the center of a non-commutative ring. So it turns out that definition that I gave last time still makes sense. As long as you take A from the center of a ring, you can still define principal ideal generated from an element which is in a non-commutative ring. So like in non-commutative, let's say possibly not commutative are if you have A is in the center of the ring, then AR is actually equal to RA, and you could still denote this by this. It would be the principal ideal generated by A. A proof very much like the one I went over last time proves that that is in fact an ideal. All right. So that's point number one. Theorem 2 states the following. The following are equivalent. Now we had part of this last time, but it bears repeating. Following are equivalent for an ideal A of a ring R. Number one, one is in the ideal. Number two, A contains a unit. Number three, A is equal to R. So the thing we went over last time was that if one is in the ideal, then it generates the whole deal, the whole thing, the whole ring. So let's think about the proof of Theorem 2. If we think about the proof of Theorem 2, certain things are obvious, right? 1 implies 2, duh, right? I mean, 1 is a unit, so if 1 is an A, then A contains a unit, yay. Also, 3 implies 1, similarly easy, right? 3 implies 1 is actually pretty clear because if A is equal to the whole ring, then of course it contains 1, right? I shouldn't even write duh that time. It's so obvious. It should just be period or something. I don't know. So let's look at 2 implies 3. If we can get 2 implies 3, that would complete the proof, right? Because then we'd have full circle. 1 implies 2 implies 3 implies 1. So we get equivalence. So all that's missing is this. So let's assume 2 is true, right? In other words, assume that A contains a unit. Right? Then if we look at U inverse, that's equal to 1, right? I mean, by definition of unit. But what are we looking at here? Think about it. U is in A, right? This is in R. But what's the definition of an ideal? If we take something in the ideal and we multiply by something in the ring on either side, we're back in the ideal again, right? So the fact that U inverse is equal to 1 implies that 1 is in A. So, all right. Great. Let R be in the ring, right? And then consider that R is equal to R times 1, right? But again, R is in the ring, where's 1 in? Yeah, this is in R. This is in A. So by definition of ideal, this is an element of A again. So that shows that every element of the ideal is in the ring. Excuse me, the other way around. That shows that R is a subset of A, right? But we already know that A is a subset of R by definition of ideal, right? So this implies that A is equal to R, which of course is item 3. So there you go. There was a tiny bit missing there from last time. Example 4 is pretty nice. Here we look at the annihilator. So let A be in the center of a ring. He defines the annihilator of A, or you could say Anna. Actually, you shouldn't say that, it's stupid. R is in the ring such that Ra equals to 0. Again, something stupid to say. So allegedly, this is an ideal. So he's playing the same game here with this example that he played with the definition of principal ideal, which is he's really studying something that's more naturally found in commutative ring theory in a non-commutative setting by just picking something in the center so that it still makes sense. Kind of sneaky, the idea of this example. But anyway, so to prove it's an ideal, we can use the ideal test that we looked at last time, right? What do we need to do? We should do what? Let's let x and y be in this thing. What do we need then? First of all, we need it's a subring, right? So if we look at r times x minus y, what happens? Let r be in the ring, okay? R times x minus y by properties of, axioms of the ring. This is rx minus ry. But remember, x and y are in the annihilator, so those are separately in both 0. So this is 0 minus 0, also known as 0, which shows you what? X minus y is in the annihilator of A. So that shows it's a subring. Then what do we need? Or subrung, I should say. We need to check the so-called Uber closure. So again, let R be in the ring. And if we consider, bless you, Rx, right? I want to see if that times A, I want that to be 0, right? That's the condition which is needed in order for Rx to be in the annihilator. I got to see when I multiply by A on the right, does it go to 0? Well, yeah, because this is by associativity that, which is R times 0, which is 0, right? So therefore, Rx is in the annihilator of A. But that's not enough, right? This is a non-commutative setting in general. I mean, this R doesn't have to be commutative, right? So I also need to check that XR times A is equal to 0, right? Because I need both XR and Rx to be in the annihilator. Both conditions I need. So I guess it's probably worth repeating definition. A, an ideal requires what two things? Number one, we need that A is sub group of R additively. In other words, it's a subring. Well, I guess it's not quite that, but good gracious. Additive subgroup, additively. And number two, we need that RA and AR are elements of A for all A and A and R and R. Now this is not a terribly useful definition for us for the current example because A is playing a slightly different role, isn't it? A is a fixed but arbitrary element we're calculating the annihilator of. So sorry to not be directly useful. Anyway, getting to the point here, this is what? What can we do? What is, A is where? It's in the center, right? So it commutes with everything. So this is XA times R, which is 0 times R, which is 0. Therefore, XR is the annihilator of A. Hence, the annihilator of A is an ideal of R by the ideal test that I stated last time. Any questions? Oops. So let me remind you something. If we have an idempotent, right? If we have E squared is equal to E, right? For some E in the center of the ring, then if you look at that, A equals to RE is what? This is actually not a reminder. This is probably more properly an observation. The reminder is coming next. Observer? No. Observe, there. This is what? This is the principal ideal generated by E. An example, Schneikes. Well, the thing that I did last time, slightly modified, is what's called example 3, which says that the principal ideal is in fact an ideal. So this is an ideal. And more than that, remember, this is the part that's a little bit maybe, this is the remembering part. What is E? E is an element of A. Serves as what for A? And we also had that RE was equal to ERE in this case. Right. So we could say it's the 1 sub A. Now A is not a subring because E is not the identity in the ring, right? But it is a subset which is itself a ring in a kind of natural way. So example 5 brings to us the following observation, that if we have A is an ideal of a ring R, right? And suppose that E is equal to the identity for that A, all right? Then in that case, E is in the center of the ring, the whole ring R, and it's an idempotent. And thus, A is equal to ERE. This is example 5 from section 3.3. So the proof is kind of fun, I mean, I don't know. What can I say about it? It's straightforward enough. It's one of these proofs that if I didn't have the book in front of me, it'd probably take me a lot longer because the construction of the proof is a little bit, I mean, it's simple if you know it, but if you don't, I don't know. I guess it might not be that bad. You just have to sit and tinker with it for a while. But we're assuming that E is the unity in the ring A, right? So EE is equal to E, among other things, right? And for any R in the ring, we can construct the following element of A, big A. We'll call that element little a. Little a is equal to plus minus ERE. Sorry, it's ER minus ERE. Okay, great. Now, so if you look at that, why is that an element of A? Can you guys tell me? Well, E is in A, right? If it's an identity for A, it's certainly in A. And anything in A times anything in the ring is in A again. So this is an element of A. And this, again, is an element of A because of the so-called Uber closure. Then we're looking at the difference of things in A, which is again in A because A is a subgroup, additively speaking, of the abelian group structure, which is the ring. Yes?
Is that E times R times 1 minus E?
I mean, it's lots of things, but so here we have A is equal to AE, right? But A is also equal to what? EA, right? And so from AE, we get what? We get ERE minus ERE squared. From EA, we get E squared R minus E squared RE, right? But these are both what? ERE equals to minus ERE, right? Oh, I'm sorry. I'm not sure that actually the second one is helpful here. I may need a different A. I need a different A. That's what it is. I'm sorry. Scratch the second equation. I don't think it's actually helpful to us. Sorry about that. But that, right, I just used E squared is equal to E, but of course that's 0, right? A is 0. So that tells me what? ER is equal to ERE, right? And then maybe we should look at like B. What would we make B? How about RE minus ERE, right? And if we look at, that's again an element of A, right? And so on the other hand, I have B is equal to EB, right? Which is equal to ERE minus E squared RE, right? Which again is 0 because that's ERE minus ERE. So that implies that B is 0, which is to say that RE is equal to ERE. So you put these two things together, what do you got? Right? What's that say about E? For which R in the ring? Arbitrary R, right? E is in the center of the ring. So and the rest of it's pretty straightforward. Basically, the rest of it, the interesting part of the rest of it follows from this earlier discussion of the corner in the ring. Yeah. I don't know. So to my taste, it's kind of a weird little example, but there it is. Example 6. So this was example 5. Example 6 we covered last time, but I would encourage you to look at example 6. I would also encourage you to use this notation for the Gaussian integers. This is not equal in common group theory terminology. This is something else. This good, that bad. Sorry, it aggravates me. So Z adjoin I, the Gaussian integers, this is A plus BI such that A and B are integers. And example 6 looks at the principal ideal generated by 2 plus I. That's exactly the thing I looked at with you guys last time in the picture. So he studies the ideal generated by 2 plus I, and he shows carefully that it's in fact a thing with 5 elements in it, and that he references an earlier theorem, which is that if we have a ring that has a prime number of elements, it has to be what? It has to be an integral domain. So, actually, I think it has to be a field. Yes?
So for problem, I guess, 69, that uses the Z adjoint W. You want us to use the right notation there?
Yes. So in the homework, I would like for you to, anytime he takes ring and he writes parentheses, omega, something like this is not standard or good notation. He should be writing brackets omega. This means the field formed by, like, it's the field that includes R as a subring and this element omega. And this, when you write the curly brackets, the parenthetical brackets, that references a field. It's something bigger. All right.
So in that example, the R square brackets omega would be embedded in the parentheses one.
Right, yes. Indeed, this would be a proper subset of this thing. Because if you go looking for the fractions that are formed like this, right? Well, going back to here, these, what are these? Well, these are things like a minus bi over a squared plus b squared, right? Which is really an element of Q with I adjoined, which is bigger than Z and I adjoined, right? So, okay. Yeah? No? Okay. Moving along here. So I defined prime ideal for you guys last time, right? And this time I will go over a theorem. What was our definition of prime ideal? You guys remember? We say an ideal is prime if what? I guess I'll remind you then. Definition. An ideal of commutative ring, let's say ring R, is called a prime ideal if P not equal to the ring, and P has for A comma B in the ring, if AB is in the ideal, then that implies that A is in the ideal or B is in the ideal. So what's this reminiscent of in number theory? Is this Euclid's lemma? I mean, I'm trying to remember what the name of this. If I have that a product of numbers divides a prime, then that means that one thing or the other in the product has to divide the prime. What's that called? Oh, okay. Well, it shall remain nameless then. Theorem. I think it's Euclid's lemma. If R is a commutative ring, all right, and ideal P not equal to R is a prime ideal if and only if R mod P is an integral domain. All right. So the proof here. Let's go with the forward direction. So suppose P is prime ideal. Right? To prove that, first of all, R mod P is commutative, right? And suppose we need to pick 2 points in there, right? A plus, let's suppose A plus P and B plus P are in R mod P with what? Their product being what? 0, right? Now that's 0 in what? That's 0 in the factor ring. So you could say that's 0 sub R mod P, which more to the point is P. P serves as the 0 in the factor ring. P is the additive identity here. Okay, so what's this say? This says that AB plus P is equal to P. Right, so what's this say? This means that AB is where? In P. Right, but P is a prime ideal, right? So this implies that either A is an element of P or B is an element of P. But what does that mean? Right, that means that P plus A is equal to P or P plus B. Oh, I'm sorry, other way around, right? A plus P is equal to P or B plus P is equal. What am I looking? Yeah. B plus P is equal to P. Which is to say that one or the other of them is 0 in the factor ring, right? So if I have the product of things is 0 in the factor ring, one or the other of them is 0, that says it's an integral domain since it's clearly commutative. So R mod P has no non-zero zero divisors. That is, R mod P is integral domain. All right? How about the other direction? Suppose that R mod P is an integral domain. Right? And suppose let the A and B be elements of the ring with AB an element of P, right? I need to show that either A is in P or B is in P. Notice that AB plus P, right? Well, first of all, notice that AB plus P is equal to P, right? So this is equal to, yes, but I'm writing it this way, A plus P times B plus, because people need to understand the substructure here. But yes, you're right, it could be, a large part of this could be made biconditional. Don't disagree with you. The reason I'm doing two directions is to try to draw attention to both of the definitions we're using. It is admittedly not the most clever proof. So let's see here. AB plus P is this times that. But what's that mean? Now I've lost track of what I was doing. Oh, right. So this is P, right? So this implies that either A plus P is equal to P or B plus P is equal to P, because why? Since, right, R mod P is integral domain. And that, of course, is it. That means A is an element of P, or B is an element of P, which then says that P is prime. P is a prime ideal. At this point, we reach theorem 4. Theorem 4 is kind of the ring. It's kind of the ring equivalent of the correspondence theorem. And essentially what it says that if you look at ideals of a factor ring, then they interface in a natural way with supersets of the thing you're factoring by. It's easier for me to write down than to say theorem 4, the proof of which is totally uninspiring, so we'll skip it. Let A be an ideal, but we do need to know these results. A be an ideal of R. Number 1, B is an ideal of R with a subset of B, then B divided by A, or B mod A, if you will, is equal to B plus A, such that B is in B, forms an ideal of R mod A. Number 2 says that if you look at funny looking B, cursive B, any ideal of R mod A basically has to arise, as we already saw in number 1. It says that all of the ideals of the factor group appear as factors of supersets. In particular, then B is equal to B mod A, where rather for some, and this is unique, B, excuse me, a subset of B. Moreover, in fact, this B has the form as follows. B is just equal to B in the ring, such that B plus A is in script B. So the way that script B appears is kind of in the most unexciting way possible. And then 3, if you have B and B1 are ideals of R, all right, containing A, then we have that B is a subset of B1 if and only if B mod A is a subset of B1 mod A. You notice the reversal of the inclusion there. Factoring reverses inclusion. B is a subset of B1, but B mod A is a subset of B1 mod A. That's not a typo. Okay. Again, the proof is on page 183, and it's pretty routine. Definition. R is simple, all right, if R is not equal to 0 and the only ideals of R are 0 and R. All right. So the example he gives here, I need to throw this thing out. It is, you don't understand. It is stout. Oh man, goodness gracious. Example 8. Every division ring is simple. What's a division ring? It's a field, but not necessarily commutative. That's funny. I like that you base everything on what we know, which is fields. It's good. It's good. Yes, everything has everything except for 0 has a multiplicative inverse, but it doesn't have to be commutative, right? So let's see here. So let A, let A be in this division ring, right? And let's see here.
Wouldn't you just say let A be an ideal?
Yeah, I'm starting out wrong. Thank you. I was about to discover that. If A not equal to 0 is an ideal, right, of R, then what you're going to tell me, Zach, was what?
Any A in there is a unit, so we have
So 0 not equal to, I'll use U, is an element of A, right?
and then I think it's theorem 1, was it not theorem 2, that's equivalent to saying A is R.
Is unit. And then by the thing I just erased, right, 3 minutes ago, this implies that A is equal to R, right? Which says what? The only ideals of R are 0 and the whole thing. So any division ring is simple. And you're right, this is essentially a corollary to Theorem 2, honestly. Theorem 5. Theorem 5 says that if R is commutative, all right, then R is simple if and only if R is a field. So we already know half of this by the previous, over this, a field is a commutative division ring, right? So, right, so this is by, what did I call that? I can't read. Example 8. So we need to look at the other direction, right? So suppose R is simple, right? We'd like to show that R is a field. So let's let 0 not equal to A be an element of R, right? It's commutative because we're assuming R is commutative, right? So recall, and we actually proved this last time, that the ideal generated by A, that's an ideal, right, is an ideal of R. Could that be the zero ideal? Notice that A is an element of A, right? Right, because it's A times 1. So that shows you that it's not 0, because we assumed A is not 0, right? So this is not equal to the 0 ideal. We assume that it's simple. What's that say? Right, so thus A is equal to R, right? Hence, 1 is an element of the principal ideal generated by A, which is to say that there exists B in R with AB equals to 1, which is to say what? Indeed, A is a unit with inverse B. And so what's that say? Yep. So that gives us that it's a field because we just showed that an arbitrary non-zero element of this commutative ring has a multiplicative inverse, which is to say it's a field. Yeah. All right. We're getting there. Definition. An ideal M in a ring R is called maximal if M is not equal to R, all right, and the only ideals A of R such that M is contained in A is contained in R, A equals to M, and A is equal to R. So the theorem that's important to know about maximal ideals, I'll write over here. I'll write over here. This is theorem 6 of section 3.3. And it says this: let A be an ideal of a ring R all right, then A is maximal, all right, if and only if R mod A is a field. Oh, I'm sorry. Sorry. Is a simple ring. You see, Nicholson has changed the cadence of my thinking a little bit here. Then when you pair that with this, right? So I'll work on the proof of theorem 6 here for the next minute or two, but if you take theorem 6 and you combine it with this, right, and you tack on the condition of commutative, what do you get? Every maximal ideal of a commutative ring gives a quotient which is a field, and only then. So R mod an ideal is a field if and only if A is a maximal ideal of a commutative ring. Okay. But he's taken the care to develop some of these theorems in the non-commutative context a little bit, so here that is. So here it is. Assume A is maximal. All right. Let B mod A be the ideal of R mod A such that what? Right. Where B is the ideal. Then what? We're trying to show what? We're trying to show that R mod A is a simple ring, right? So what we're doing is we're looking at an ideal of R mod A. What's our goal? Our goal is to show either that ideal is 0 or it's the whole thing, right? So let's see here. He says since B over A, oh, A is maximal, was part of the definition of maximal what? Well, I didn't say M is not equal to 0. Well, anyway. I'm not quite clear why. Oh, I'm sorry. I just missed a word. Very important word, which was about to confuse me needlessly. Non-zero. There it is. So to say that that's a non-zero ideal is basically to rule out the case what? A equals to B, right? If A is equal to B, then that's the 0 ideal. Anyway, since B over A is by assumption not equal to 0, that tells us that B is not equal to A, right? So, I mean, he says let 0 not equal to B plus A be an element of B mod A. That implies that B is an element of B and B is not an element of A. So this thing I just wrote is the explanation for this implication, okay? This right here is because of that sentence. That sentence shows that the sets are not equal. All right? In other words, he's showing non-equality in the factor group implies non-equality of the sets. That's all. Nothing more than that. Thus, A is not equal to B. Hence, B is equal to R. Why? Because we had what? We have A is a subset of B is a subset of R, right? So by maximality of A, B has to be R, right? So then what? Thus, B mod A is equal to R mod A, right? We just showed then that any non-zero ideal in the factor ring has to be what? Has to be the whole factor ring. That's by theorem over there, that if we have B mod A is the ideal of R mod A, then there exists a B containing A such that it gives the quotient as advertised. So that's using either 1 or 2 of theorem 4. I'm not.
Right, I
Yeah.
understand that we can take B mod A and then get B, but how do we know that B is going to be a superset of A?
This gives us the existence of the B.
Oh, for A any ideal.
Yeah,
Okay, got it.
yeah. So anyway, the other direction of this proof is very similar. I won't go over it in class. I just want to leave you with a couple more comments briefly. So the end of end of section 3.3, he talks about examples of simple rings. And so the main idea at the end of section 3.3 is that if we look at matrix rings over R, then these give simple rings. Provided what? The central theorem at the end of this section is that that's a simple ring provided that R is itself simple. Which is neat because that means that we also know that fields, like the reals, the complexes, the rationals, these are simple rings. So if you look at the matrix rings actually built over any division ring, you get examples of simple rings. All right? And then I guess I didn't get the homomorphisms, but I will leave you with this question. So one of the things we learn in the next section, homomorphisms, is this. Basically, if we have a homomorphism from one ring to another, it preserves rational expressions, is what we learn. So we have things like psi of u is equal to psi of u inverse, where that's assuming that u is an element of the units in the ring, right? So I claimed the other day that if we had an algebra isomorphism, that it had to have homogeneity, right? I said that if we had psi of cx, that I could write c psi of x for cx in real algebra, right? Like we actually calculated the possible isomorphisms between the hyperbolic numbers and r cross r, right? I used that this had to be a property for those isomorphisms. I would point out to you, in section 3.4, we can easily prove that psi of a rational number, all right, times an element should be equal to that rational number times the element, provided that if you have a copy of the rational numbers inside your ring, all right? In other words, if you can add and divide by number, if there's a copy of the rationals inside your ring, you can pull Q out through pretty simple arguments. My question then is, how on earth do we get to pulling out real numbers? Because that apparently is something, I'm telling you it can be done. I'm also telling you that this is actually a pretty challenging thing to prove. The thing I got stuck on the other day, in terms of proving that I could pull out the C, it's actually non-trivial. And it's where this course meets real analysis. So anyway, something to think about. I shut up. See you guys.